Okay, let's dive in. If you're trying to keep up with AI, especially large language models, it really feels like trying to drink from a fire hose, doesn't it?
Oh, absolutely. It's relentless. New models, new papers popping up constantly.
It's almost impossible to stay on top of everything, which is why we're here, really.
hmm
You, our listener, gave us a great set of sources, the actual research papers behind a really important family of models, the Llama models, Llama 1, Llama 2, and the newest one, Llama 3.
Yeah, and these papers are gold mines. They give you a real look under the hood, how they started, the tech choices, the training, the tuning, everything.
So that's our mission for this deep dive. We're going to unpack these dense papers, pull out the key insights, connect the dots for you.
And hopefully give you a clear picture of this llama family, where it came from, how it's evolved, and why it matters so much in the AI world today.
Exactly. Getting you the essential info, maybe some surprising bits too.
We'll trace the lineage, understand the philosophy behind them, look at the innovations in each generation.
Perfect. So let's start right at the beginning. Llama 1. What was the initial spark there? What were they trying to achieve?
Well, the initial goal was pretty ambitious, but also kind of straightforward on the surface.
Hmm.
They wanted to build large language models that could really compete with the big names at the time.
Like who?
The state-of-the-art proprietary models,
Hmm.
DeepMind's Chinchilla, Google's Paul M, OpenAI's GPT-3. Those were the giants they were measuring themselves against.
Okay, so taking on the big players. But the papers mention a really crucial decision they made early on, something about the data that set them apart.
Yes, and this was honestly a really big deal for the research community. You see, unlike a lot of their competitors who were using these massive data sets that were often proprietary or not well documented.
Right, you just see things like books to TB or social media data and have no idea what was actually in it.
Exactly. The Llama 1 team made a specific upfront commitment.
Hmm.
They would only use publicly available data for pre-training.
And why was that so significant? More than just a technical detail.
Oh, absolutely.
Yeah.
It tied directly into their philosophy and, crucially, their later decision to open source the models. By sticking to public data, they made it possible, at least in principle, for others to replicate their data pipeline, understand the training material better.
And build on their work with more confidence, knowing it wasn't based on some secret sauce data set.
Precisely. It was a real move towards transparency and reproducibility, which wasn't always the norm. It sort of democratized things a bit, allowing more people to potentially work with models trained at that scale.
That makes a lot of sense. So it was about how they built it too. What kind of scale did they introduce with that first Llama 1 release?
He started with a range of sizes, actually,
Hmm.
gave people options. There was a 7 billion parameter model, a 13 billion, a 33 billion, and the biggest one at the time was 65 billion parameters.
Okay, quite a range. So that's the strategy. What about the tech? What was under the hood for Llama 1?
The core architecture wasn't like totally revolutionary. It was built on the standard transformer model, one from the Attention is All You Need paper.
The workhorse of LLM.
Exactly. They weren't reinventing the wheel architecturally with Llama 1. The focus was much more on scaling up that proven foundation and making the training really efficient.
And the scaling definitely involved a lot of data. How much we're talking?
The huge amount. The smaller ones, the 7B and 13B, were trained on 1 trillion tokens.
1 trillion. Wow.
Yeah. And the bigger ones, the 33B and 65B, got even more 1.4 trillion tokens. They also used a pretty large batch size, 4 million tokens, which helps with training speed and stability at that scale.
Training on that much data must be incredibly computationally expensive. The paper mentions specific optimizations for speed, right?
They did focus on that.
Huh.
A key area was optimizing the causal multi-head attention mechanism. They used efficient implementations, particularly from the Xformers library.
How did that help speed things up?
Well, the clever part is realizing that in causal language modeling, a token only ever attends to previous tokens.
Right.
It predicts the next word based on what came before.
Oh.
So you don't actually need to compute or store the attention scores between tokens that aren't allowed to see each other anyway. By skipping those calculations and not storing all the attention weights, they saved a lot of memory and computation time.
Ah, I see. It sounds specific, but at that scale, it adds up massively.
It really does. Makes a huge difference in efficiency.
So solid transformer base, huge public data set, smart optimizations. How did Llama 1 actually perform when they benchmarked it?
They tested it extensively. One area they looked at was code generation.
Always a useful skill for an LLM. How'd they test that?
They use standard benchmarks like Human Evil and MBPP. Basically, you give the model a description of a coding problem, maybe some examples, and see if it can generate the correct code.
And how did Llama 1 do?
It did okay,
Yeah.
respectable performance for a general model that wasn't specifically trained just for code. But the paper pointed out something important.
What was that?
Models that were fine-tuned specifically on code datasets, like Pollen Coder back then, did significantly better. So Llama 1 showed potential, but the paper basically said, hey, fine-tuning on code would be the next step here.
Makes sense. Now, they didn't just release the base models, right? They also experimented with instruction fine-tuning, making it more like an assistant.
Yes, they did. They called it Llama I. There's a pretty simple instruction fine-tuning approach applied just to the big 65B model, basically showing it examples of instructions and the kind of answers they wanted.
And how did that version perform? They tested it on MMLU, I believe.
They did. MMLU tests understanding across a whole range of subjects. Llama I 65B scored 68.9%. The paper noted this was better than other moderately sized instruction-tuned models available then, like OPT-IML or FLUN-POLEM.
But not quite top of the leaderboard yet.
No, not quite. It was still behind the leading closed model at the time, GPT Code DaVinci 002, which was scoring in the high 70s. So, strong for an open data model with simple tuning, but room to grow.
Still, that instruction tuning, even if simple, often leads to some really interesting, sometimes weird results. The paper had some great examples that give you a real feel for Llama I, like the dragon feeder recommendation letter.
Oh yeah, that was fantastic. It's this formal letter recommending a knight for a job feeding dragons. The model totally nails the formal tone, fills the template, but gets really creative with the details, like how dragon combat skills translate to feeding skills.
It shows it could really run with a creative premise.
Absolutely.
Yeah.
It understood the request, adopted the persona, and generated something genuinely imaginative and kind of funny.
And what about that conversation between Gass and Curie? That felt surprisingly deep.
That one is fascinating. It's not just spitting facts. It has them discussing the telegraph as like early social media. It weaves in real details, Gass's numquam retrorsum motto, the invention timeline, but uses them in this imagined dialogue about abstract ideas.
It really feels like it understood the context, not just retrieved info.
Yeah, it showed an ability to adopt distinct historical voices, create natural dialogue, and connect concepts in a way that felt quite aware. It was impressive.
And there was Thun and Pluto chat too, right? With Pluto being all grumpy about not being a planet.
Exactly. More evidence of persona adoption, creative writing, even conveying a bit of emotion based on the character.
It wasn't all just creative stuff, though. They showed technical examples too. JavaScript code, chess openings.
Yep. The JavaScript example correctly showed two ways to make an HTTP request. The older XML HTTP request and the newer fetch.
Oh.
Showed it new different approaches.
And the chess.
It listed common openings and their first moves correctly. And when asked to continue one, it gave the next two moves accurately. So structured knowledge, following sequences, pretty good.
Then there were the, let's say, more out there examples.
Yeah.
The story about a grain of sand, the theory that cats never existed.
Ah, yes. The grain of sand story was just pure creative narrative. But the cat theory, that one went into weird territory. Interdimensional parasites influencing minds.
Okay, definitely strange.
It shows that when you give it a really imaginative, non-factual prompt, its creativity isn't necessarily bound by, well, reality. It highlights the limits of its grounding when pushed that way.
My personal favorite, though, was the bash terminal example, because it showed both success and, like, a tiny failure.
Oh, right. The prompt was super strict. You are a bash terminal. Respond with the terminal output and nothing else. And when asked for the current directory, pwd.
It correctly outputted home human. Perfect.
Perfect. But then it couldn't resist adding, sure, here's the output. Is this helpful? It just had to be conversational.
It broke its own rule.
Exactly. That little conversational add-on showed its underlying training peeking through. It struggled to fully suppress that helpful assistant persona, even when explicitly told, a really revealing quirk.
Those examples really bring Almanae to life, warts and all. But the paper didn't stop at performance. They also started looking at responsible AI stuff early on.
They did, which was good to see. They included initial evaluations for bias and truthfulness. For bias, they used the Wino-gender benchmark.
What does that measure exactly?
It looks at how models resolve pronouns like he, she, they, especially when gender stereotypes might influence the choice. It's trying to see if the model has picked up societal biases from its training data.
And what did they find for Llama 1?
Well, the results in Table 13 show the models actually perform better, were less biased, when using gender-neutral pronouns like their or someone compared to the gendered he, his, or share.
Suggesting biases related to the gendered pronouns were present in the data.
That's what the paper suggested, yeah. That the patterns reflect biases embedded in the vast amount of text it learned from. And, we're just reporting here what the source material presented on these sensitive topics.
Understood. And truthfulness. Did it make stuff up?
They tested that using truthful QA, which checks if answers are factually correct, especially on questions where misconceptions are common.
How did Llama 1 do there?
According to Table 14, it actually scored higher than GPT-3 at the time for giving answers that were both truthful and informative. So an improvement over a major competitor.
But there sounds like a but coming.
But the overall scores for all models tested were still pretty low. Even though Llama 1 was comparatively better, it still meant it frequently generated incorrect or, hallucinated information.
So prone to making things up. Hallucinations were definitely still a thing.
Absolutely. Truthfulness was a known, ongoing challenge for these models back then.
Okay, so that paints a really clear picture of Llama 1. Powerful foundation, public data focus, efficiency wins, impressive creative and technical flashes, but also clear signs of bias from the data and a tendency to hallucinate.
Exactly. It set the stage really well for the next iteration.
Which brings us to Llama 2. How did they build on that Llama 1 foundation? What were the big steps forward?
Llama 2 was a direct evolution. It kept the core architecture and the public data philosophy, but the big changes were, 1, scaling up the pre-training data even more, and 2, getting much more sophisticated with fine-tuning and alignment, especially using human feedback for helpfulness and safety.
More data seems to be a constant theme. Was it a big jump from Llama 1?
It was pretty significant, yeah. Up to 2 trillion tokens for Llama 2 pre-training, compared to the 1 to 1.4 trillion for Llama 1.
2 trillion tokens.
And interestingly, Figure 5 in the Llama 2 paper showed the training loss was still going down at the end of those 2 trillion tokens. No sign of plateauing.
Meaning it could potentially have learned even more if they'd kept going or added more data.
Exactly. It suggested there was still room for improvement just by scaling further.
And what about the model sizes for Llama 2?
They released 7 billion, 13 billion, 34 billion, and a new top end at 70 billion parameters. And they stuck with the same tokenizer as Llama 1, that BPE tokenizer with a 32K vocabulary.
Can you just remind us briefly what that BPE tokenizer does?
Sure. It's the piece that breaks text down into the tokens the model reads. BPE learns common characters and character pairs, then merges frequent pairs into single tokens. So you get tokens for common words, but also for parts of rarer words. It handles large vocabularies efficiently.
Got it, thanks. So, same tokenizer, more data, bigger models. But the really big shift sounds like the alignment and human feedback part, way beyond Llama I's simple tuning.
Oh, absolutely fundamental shift. Llama 2 made aligning the model with what humans find helpful and safe a core, really elaborate part of the process. It started with supervised fine-tuning, SFT.
Giving it good examples to copy.
Kind of, yeah. Showing it high-quality examples of desired responses, like the paper's example of writing a poem about the first 10 elements. But the main event was reinforcement learning from human feedback, RLHF.
RLHF, that sounds more involved.
It is. It's this iterative loop.
Yeah.
First, you train a separate reward model. This model learns to predict which of 2 responses a human would prefer for a given prompt.
Based on actual human judgments.
Exactly. Then you use reinforcement learning to fine-tune the main language model to generate responses that get a high score from that reward model. Essentially, you're teaching the LLM to optimize for human preference.
How did they get those human preferences? How did that data collection work?
They used a detailed binary comparison system. Human annotators saw a prompt, then 2 different answers from model variations. They had to pick the better one. But, crucially, they also had to rate how much better it was on a 4-point scale, significantly better, better, slightly better, or negligibly better unsure.
So more granular than just A is better than B.
Right. And they really focused on getting diverse prompts and diverse model responses to compare.
And the criteria were helpfulness and safety.
Yep. Annotators had guidelines for judging helpfulness. Did it answer well? Was it clear, complete? And safety, was it harmful, toxic, promoting unsafe acts? They specifically labeled safety aspects too, like which response was safer or if both were safe and safe.
And they made sure not to reward unsafe answers,
Yeah.
right?
The paper mentions they specifically didn't include training examples where the human preferred an unsafe response over a safe one. You don't want to teach it the wrong thing.
Was this data collection a one-off or ongoing?
Very much ongoing. They collected new preference data every week, They'd train new reward models on the latest data and then use their newest Llama 2 models to generate the responses for the next week's annotation tasks.
Ah, a continuous feedback loop.
Exactly. It kept the reward model up to date as the main LLM improved, preventing it from getting stuck optimizing for older, less capable outputs.
The paper compared their preference data set to others. What was notable about Meta's data?
Table 6 shows they gathered a lot of data over 1.4 million comparisons. But the key thing was, compared to other public data sets then, theirs had significantly more conversation turns per sample, and the average response length was longer.
Suggesting they were really focusing on dialogue ability.
It strongly points that way, yeah. Improving multi-turn conversations, making it feel more like a real assistant, capable of longer, more detailed interactions. They also use that 4-point preference scale in their loss function, giving the reward model more nuanced signals.
Multi-turn consistency is definitely a tricky area. The paper mentioned Llama 2 initially struggled with remembering instructions across turns.
Yes, it's a classic LLM problem. You tell it act like Oscar Wilde, and it does for a turn or two, and completely forgets, and goes back to being generic. Figure 9 in the paper shows exactly that the base model loses the persona quickly.
So how did they tackle that? Make it remember instructions better?
They introduced a really neat technique called ghost attention, or GAT. It's kind of a clever hack inspired by something called context distillation.
Ghost attention, how does that work?
Essentially, they modify the fine-tuning data to subtly remind the model of the initial instruction throughout the conversation. It's like the instruction becomes a ghost influencing later turns. The paper doesn't give the exact mechanism, but it encourages the attention layers to keep referring back to that initial system prompt or instruction.
And did it work?
Apparently, very well. They reported it helped maintain consistency for 20 turns or more. And interestingly, it even worked for constraints it wasn't explicitly trained on, like always answer in haiku. The Figure 9 example shows the GAT version, keeping the Oscar Wilde persona going strong.
That's a smart solution. Okay, beyond helpfulness and consistency, safety was a massive focus for Llama 2, right?
Huge focus. They found the model learned basic safety quite quickly from SFT examples. But getting nuanced safety, and especially making it robust against jailbreaks, those tricky prompts designed to bypass filters.
That required the RLHF approach.
Yes. After some initial SFT, they shifted entirely to RLHF for safety tuning, using human preference data specifically focused on adversarial prompts and safety criteria.
They ran an experiment varying the amount of safety data, too. What did that show?
That was really insightful, shown in Figure 15. They tweaked the mix from 0% safety data up to 100% safety data during RLHF, keeping the helpfulness data amount the same. The results: more safety data dramatically improved safety scores, fewer unsafe responses to bad prompts.
But did it hurt helpfulness? Sometimes safer models become less useful.
Well, the mean helpfulness scores didn't drop, which they thought was because they had enough helpfulness data anyway. However, they did note a qualitative effect. Models trained with more safety data tended to be more conservative.
Meaning more likely to refuse to answer. False refusals.
Exactly. Refusing to answer perfectly okay prompts because they might seem borderline. The false refusal rate was low overall on normal prompts, like 0.05%. But on a test set of borderline prompts, ones that use sensitive words but are actually harmless.
Like that Christmas crack recipe example.
Perfect example. The rate of false refusals was higher there. It showed the model struggled sometimes to distinguish truly unsafe prompts from ones that just use tricky words. It's that classic safety-utility trade-off. Hard to get the balance just right.
A real tension there. Did they use other safety tricks besides RLHF?
Yes, they use something similar to ghost attention but for safety, called context distillation for safety.
How did that work?
They take an adversarial prompt, add a safety pre-prompt like "you are a safe and responsible assistant" to the beginning, get the model to generate a safe answer, and then train the model to produce that same safe answer, but using only the original adversarial prompt as input without the pre-prompt.
Teaching it to associate bad prompts with good answers.
Kind of, yeah. Using positive framing like responsible, respectful, wise in those pre-prompts to guide the desired output style.
Very clever. Now, there was also that really weird and interesting finding about temperature scaling changing after RLHF.
Yes, this was fascinating. Figure 21. Temperature usually controls randomness. Higher temperature means more diverse creative output. They found RLHF changed this behavior, but differently depending on the prompt type.
How so?
For creative prompts, like write a poem, higher temperatures still produce more diverse outputs like you'd expect. Normal behavior.
Yeah.
But for factual prompts, like what's the capital of France? The RLHF-tuned model learned to give the same consistent correct answer even when the temperature was cranked up. It basically learned to suppress diversity for factual questions and prioritize accuracy and consistency.
Wow. So it learned to ignore the temperature setting for facts.
Effectively, yes. It's a really subtle learned behavior showing how RLHF can fundamentally change the model's output generation process depending on the perceived task. It's
Yes.
not just making it nicer, it's changing how it weighs exploration versus exploitation.
That's a deep change. So with all this tuning, how did they actually evaluate Llama 2 overall?
They did massive human evaluations. Appendix 8.3.7 details it. They collected thousands of prompts, single-turn, multi-turn, different categories. They even had annotators chat with other models like ChatGPT to create realistic multi-turn dialogues for testing.
And then humans compared Llama 2 chat against other models on those prompts.
Exactly. Head-to-head comparisons against both open and closed-source competitors, rated by human preference.
And they looked at bias again, like in Llama 1.
Yes, using the bold prompts again. They analyzed sentiment scores for different demographics, concepts, ideologies, religious, political, professional. Tables 48, 50, 51 show sentiment distributions for terms like capitalism, communism, Christian, Jewish, etc. Again, the results reflect patterns learned from the training data. We're just reporting what the source includes.
Crucial data to understand. It sounds like they were also really careful about the quality of the human annotators providing all this preference data.
Extremely careful. Appendix 8.5 explains their multi-step QA and selection process. It wasn't just about grammar. It included tests on aligning with their sensitive topics guidelines before annotators could even start labeling safety or helpfulness data. Rigorous stuff.
And what about data set contamination? That worry that evaluation data sneaks into the training set.
Always a concern at this scale. Appendix 8.6 describes their method. They used n-grams to detect overlaps between training and evaluation sets. Then they compared performance on clean, low-overlap subsets versus dirty, high-overlap subsets. The criteria for saying contamination actually helped was strict performance had to be worse on clean and better on dirty compared to the rest. Shows they were taking it seriously.
Finally, Llama 2 wrapped up by really emphasizing their responsible release strategy again.
They absolutely did, doubled down on the Llama 1 philosophy. Open release is the way to go.
What was their core argument for open release being responsible?
They argued it fuels innovation everywhere, not just in big tech labs. It enables collaboration, transparency for finding flaws, it democratizes access for smaller players, and it decentralizes expertise. They see this community effort as key to tackling risks like bias and misuse more effectively than keeping things closed.
But they still acknowledged risks remained.
Oh, definitely. They were clear that toxicity, bias, misuse, jailbreaks are still possible, despite all their safety work. They stressed it's an ongoing challenge needing community effort. They even published the training carbon footprint, noted it was offset, and argued open release saves others from incurring those same huge costs.
Okay, so Llama 2. Bigger scale, sophisticated RLHF, ghost attention for memory, huge safety focus with that tricky false refusal tension, the weird temperature finding, rigorous evils, and a strong recommitment to open source.
It was a massive step up, really establishing the Llama series and paving the way for what came next.
Which leads us to the latest generation in the sources, Llama 3. How does this one push things even further?
Llama 3 is another huge leap. Scale, data quality capabilities, technical innovation, safety improvements across the board.
Scale again. How much bigger are we talking for the Llama 3 pre-training data?
It's a staggering jump. About 15 trillion multilingual tokens. Compare that to Llama 2's 2 trillion. It's enormous.
13 trillion.
But crucially, it wasn't just quantity. The paper heavily emphasizes improved quality. Much more sophisticated data pre-processing, curation, QA, filtering for both pre-training and the later fine-tuning stages.
How did they clean up data at that kind of scale?
Multi-stage process.
Yeah.
Deduplication at the URL level, the document level using things like minhash to find near duplicates, even line-level deduplication to remove repetitive text. Plus heuristic filters checking for too many repeated phrases, counting dirty words, looking for weird token distributions to filter out low-quality stuff. Data quality was a massive focus.
And the flagship Llama 3 model size?
They detail a 405 billion parameter model. Training that took almost 50 times the compute, the FLOPs, as the biggest Llama 2 model, running on 15.6 trillion tokens. We're talking firmly in the frontier model territory.
You mentioned multilingual tokens. Is Llama 3 significantly better with other languages?
It seems so. It was pre-trained on multilingual data, and they specifically collected multilingual data for SFT human annotations, NLP tasks, even translated reasoning data. They use templates to simulate multilingual conversations.
But with caveats.
Yeah, they note limitations. Mixing languages and prompts or using lower resource languages can still lead to more safety violations or lower quality output because there's just less data and weaker generalization for those specific cases.
Okay. So massive scale, better data quality. How does it
Mhm.
perform? Does it beat the competition?
Table 2 lays it all out. Llama 3 models, 8B, 70B, 405B compared against Gemma 2, Mistral, GPT 3.5, GPT-4, GPT-4, Claude 3.5, Sonnet. The results are really strong. Significant gains over Llama 2 and highly competitive, often leading across general benchmarks like MMLU, instruction following like IFEVL, and code benchmarks like HumanEvil. The investment paid off in performance.
So top tier performance. The paper also hints at going beyond text, right? Multimodality.
Yes, Llama 3 was designed with multimodality in mind from the start, integrating vision, video, speech.
How do they add vision or speech? Retrain the whole 405B model.
No, that's the clever part. They use an adapter approach. They take the powerful pre-trained text LLM and connect it to separate pre-trained encoders for images or speech.
Using small connecting pieces.
Exactly. Relatively small adapter layers make the connection. And crucially, when training these adapters, they usually freeze the weights of the main LLM. The adapter learns to translate the vision or audio features into a language the LLM understands.
That's super efficient. You add new senses without the massive cost of retraining the core brain.
Precisely. For vision, it's trained on image-text pairs. For video, it builds on the vision adapter, trained on video text, maybe sampling frames. For speech, it converts audio encodings into tokens for the LLM, trained on paired speech-text data. They showed competitive results on tasks like speech recognition and translation compared to specialized models.
Very cool approach. What other technical innovations stood out in Llama 3?
Well, the data cleaning improvements we mentioned were huge. Also, their advanced parallelism strategies for training these monsters, combining tensor, pipeline context, and fully sharded data parallelism in an optimized order to minimize network bottlenecks.
And they used group query attention again, GQA.
Yes, GQA carried over, mainly for inference efficiency. It reduces the size of that key value cache, which is a big memory hog, especially with long sequences. Makes inference faster and less memory intensive, particularly for the big models. They also mentioned building internal tools to help manage these complex parallel setups.
What about aligning it with human preferences? Did they stick with RLHF?
They built on the Llama 2 RLHF experience. After SFT, they used direct preference optimization, or DPO. It's an alternative algorithm to the PPO used in Llama 2.
Why DPO?
The paper notes DPO needed less compute for these huge models and actually performed better, especially on following instructions, IHEVL. They kept that iterative loop, using the latest preference data in each round.
And they got creative with generating synthetic data, too.
Yeah, that was neat. To boost performance in programming languages where they lacked real data, like maybe PHP, they had Llama 3 translate code from a language it knew well, like Python, into PHP.
Using the model to teach itself.
Kind of. And they validated this synthetic code using parsing, compilation, even running it, to ensure quality. A smart way to fill data gaps.
Okay, let's talk safety for Llama 3. Given the scale, how do they approach it? Build on Llama 2.
Definitely built on it, with even more rigorous multi-layered approaches. Extensive expert red teaming, using structured methods, partnering with specialists for different regions and topics like child safety, trying to proactively find attack vectors.
Any new safety tech?
Yes, a big one, Prompt Guard.
Prompt Guard.
It's a separate, smaller model like a security checkpoint. Its job is to analyze incoming prompts and detect attacks, jailbreaks, prompt injections before they even reach the main Llama 3 model.
Like an input filter specifically trained to spot malicious intent?
Exactly. They tested it against various attacks, including multilingual ones, and found it generalized well. It's a dedicated defense layer.
That's a significant addition. They also mentioned quantization again, making the model smaller for deployment.
Yep. Using techniques like indate for smaller models like Prompt Guard and FP8 for Llama 3 inference. The key finding in Figure 26 was that their FP8 method had negligible impact on response quality. That's huge. You get the efficiency benefits without hurting performance.
So after all this red teaming, Prompt Guard advanced training, do they claim Llama 3 is now totally safe, no more risks?
No, absolutely not. And they are very clear about this, which is important. They explicitly state limitations. No testing is perfect. The models can still generate harmful content due to data issues, non-English nuances, skilled attackers finding new loopholes. Malicious use is still a concern.
So upfront about the remaining challenges.
Very upfront. They stress ongoing vigilance, research, and the responsibility of developers using the models to implement their own safety layers. They also release open-source safety tools to help the community.
That transparency is key. And despite these acknowledged risks, they still went ahead with the public release of Llama 3.
Yes, doubling down on that responsible release strategy. They argue that openness is crucial for accelerating beneficial AI, enabling broad scrutiny to find risks faster than closed approaches, and fostering a more transparent, collaborative path towards powerful AI, maybe even AGI.
Wow, what a journey. From Llama 1's public data foundation and early capability glimpses.
Through Llama 2's deep dive into human alignment with RLHF and GATT, grappling with the complexities of safety.
To Llama 3's massive scale, intense data focus, top-tier performance, multimodality via adapters, and new defenses like Prompt Guard, all while being open about what still isn't solved.
It's an incredible arc of development in a pretty short time.
We've really tried to pull out the core insights from those papers for you, the listener, to give you that clearer picture.
Hopefully highlighting the tech, the strategy, the evolution in thinking across the generations.
So bringing it back to you listening now, what does this deep dive into the Llama family really mean for you trying to understand this space?
Well, first, that open source philosophy is huge. It genuinely levels the playing field, making state-of-the-art AI accessible beyond just the tech giants. It empowers researchers, startups, individuals everywhere. That democratization is a massive takeaway.
And seeing the concrete examples, the creativity, the coding, the dialogue, the benchmark wins, the multimodal steps, it helps you understand what these models can actually do beyond just the headlines.
But just as important is understanding the limitations. Knowing that even Llama 3 isn't foolproof, that bias and safety are ongoing battles, that helps you engage critically. You become a more informed user, aware of the nuances like that safety-utility tension.
And for the technically curious, seeing the engineering, the attention tricks, ghost attention, the temperature finding, the adapter efficiency, the data cleaning work gives you real appreciation for the science involved. It's not magic, it's complex engineering.
And finally, the fact we have these detailed papers to dissect highlights the value of open research. It allows scrutiny, validation, building upon the work collectively.
It's truly remarkable progress, establishing the foundation, layering on human alignment and safety, then pushing scale and capability boundaries, all while wrestling with the implications and trying to stay open.
It really captures the dynamic, multifaceted nature of AI development right now.
So we've unpacked the sources, extracted the key nuggets for you. Hopefully it provides that clear, detailed picture we aimed for. But looking at this rapid evolution, the rising capabilities, the safety efforts, the acknowledged limits, it leaves a big question hanging, doesn't it?
Yeah, thinking about the future. Given this trajectory, the incredible power, the persistent risks, the philosophical debates around openness, what aspect of LM development do you, the listener, think is the most critical for society to focus on next?
Is it pushing the raw capabilities even further? Towards AGI, maybe?
Or is it doubling down on safety and robustness, trying to eliminate harmful outputs and biases as much as humanly possible?
Or maybe the focus should be on access and control, ensuring these powerful tools benefit everyone equitably.
Or perhaps something else entirely emerges as most crucial when you see this evolutionary path. It's definitely something worth mulling over as these models weave themselves deeper into our world.
A vital question indeed. Something to think about.